department finalist, and our project is Dynamic Aware Intelligent Orchestration for Hybrid Quantum Classical Brain Simulation. Hybrid quantum classical computing systems are expected to support latency-sensitive, high-fidelity scientific workloads such as microcircuit brain simulation, adaptive operator learning, autonomous control systems, and real-time spectral analysis. Despite advances in hybrid orchestration frameworks, most current deployments rely on heavyweight middleware layers and generalization scheduling stacks that introduce significant routing overhead, persistent monitoring costs, and inefficient backend utilization. To address these limitations, this project proposes a lightweight, dynamic-aware hybrid orchestration framework that eliminates dependency on statistic, multi-layer scheduling infrastructures and enabling direct metric-driven task routing across CPU, GPU, and CPU backend. Heavyweight middleware dependence. Most hybrid deployments rely on generalized scheduling stack, persistent monitoring service, and multi-layer orchestration pipelines that introduce additional routing latency and execution overhead before subtasks reach CPU, GPU, or QPU backend. Resources inefficiency in heterogeneous systems. Continuous execution of middleware components consumes significant CPU time, memory, and coordination bandwidth, reducing the effective capacity available for numerical integration, reduced order inference, or quantum kernel evaluation. Non-deterministic subtask dispatch. Multi-stage scheduling workflows and queue-based assignment strategies result in unpredictable routing delays. Marketing short-lived or stiffness-triggered subtasks, inefficient and less responsive during critical simulation phase. Focus of area: design and development of a lightweight, dynamic-aware hybrid orchestration framework for heterogeneous quantum classical computing systems. Implementation of API-driven task lifecycle management of subtask registration, backend routing, execution control, and monitoring. Reduction of scheduling overhead by removing heavyweight middleware layer and replacing static orchestration pipelines with metric-driven backend selection. Integration of fine-grained execution monitoring of latency, backend utilization, and numerical fidelity metrics. Target audience: hybrid quantum classical simulation environments requiring low execution latency and high computational reliability. Resources-constrained heterogeneous system where CPU, GPU, and QPU resources must be allocated efficiently. Latency-sensitive and stiffness-dominated applications such as neural simulation, reduced order operator learning, and real-time scientific computation. Limitations of this project: performance depends on heterogeneous backend availability, CPU, GPU, QPU capacity. Execution latency varies with workload intensity, stiffness distribution, and concurrent task volume. API-driven routing and monitoring operations may introduce measurable coordination overhead in fine-grained execution scenarios. Requirement analysis: identify hybrid quantum classical execution requirement, routing latency, consistency, stiffness characteristics, and heterogeneous backend limitations. Testing and validation: conduct performance evaluation under varying workload intensities, stiffness distribution,